My name is Erik Knudsen. I work at the Technical University of Denmark in the physics department. My main job is developing a ray tracing code for X-ray scattering experiments and optics simulations. Most people perhaps know me as being part of the core McStas team for neutron ray tracing simulations, and the code that I develop is McXtrace is very similar. It's actually a sibling that shares a lot of code with McStas. In this particular case, it's actually branching out a little bit into ray tracing telescope simulations for space-based telescope and also terrestrial, but X-ray telescopes. I got to know McStasScript because I happen to be acquainted with Mads Bertelsen at the ESS, and also as an observer in the work package 5 of PaNOSC project. Now, McStasScript is a Python interface to McStas, which has the feature that it's rather more simple to implement a simulation where you have lots of similar objects or devices in the simulation. In a sense, it really gives access to a loop, which is kind of lacking at present, at least in the a simple way of doing that in the McStas language or McXtrace for that matter. So we had to do some edits to the McStasScript code in order to make sure that it ran using McXtrace. And particularly for telescope simulations, this looping feature is very, very useful because in that case, you often have X-ray telescopes are often based on a Volter geometry where you have lots and lots of mirrors that are largely identical, a slight change in geometry, but that's it. So and you get many of those. In the example I will be showing later, we have 2 times 133 very similar objects that just need to be added, and that's tedious and error prone if you do it by hand. So there, the scripting feature of McStasScript is extremely useful. This really springs from a number of years of collaboration between myself and the DTU Space, the space center located at DTU, or Technical University of Denmark. So the DTU Space have been part of designing this NuSTAR telescope, and also are a major part in designing a new flagship mission for the European Space Agency called Athena, which is going to be a very large telescope. The intention is to launch it in 2030. That being said, one of the main things that always needs to be done for a new telescope design is that it has to be simulated very carefully. And also one standard thing that always is done is ray tracing it. And instead of building yet another ray tracer for this particular telescope, we have been adapting what we have, the idea being that for future missions and other missions, we can reuse instead of reinvent. And that is the reason for doing that. In collaboration with the DTU Space and also ENAF in Italy, who are also heavily involved in this Athena project. So the hope is that this is going to be a standard tool for the European Space Agency. So this has been going for some years now and has been rather successful. Okay, so I will be sharing my screen. So this notebook is called Simulating the NuSTAR Telescope with AstroX McXtrace using the McStasScript Python package. So mention here in the beginning about, first of all, what is McXtrace? And then the new thing that I haven't mentioned before is the AstroX, which is basically is an add-on toolbox to McXtrace that introduces a few geometries that and devices that make sense for a telescope. We intend to include that in the normal McXtrace distribution in the future anyway. So it is going to be a very standard toolbox. Now, some talk about McStasScript, and here is then where I start setting up the simulation. I should mention that up in the top of this notebook, there is a link GitHub, where you might find this actual notebook and the data files that are there. I've made them open so that you can, if you want to, you can simply just fork or clone that repository and run the Jupyter notebook yourself. First of all, we need to import some packages necessary for the McXtrace simulations. This is just a bit of boilerplate telling us where the McXtrace path is and where the McXtrace MX run path is. And this is basically what you need to do. In my case here, I have my installation of McStasScript in this address here. This is simply where I've forked, or rather cloned, my Mads Bertelsen's original Git repository for McStasScript. You don't need to install anything more fancy than that. So I'll just run this cell. Now we can start setting up our instrument. And the first thing we need to do is to instantiate the instrument itself. An instrument is terminology for the basic setup, or the geometrical setup that we have. I call this NuSTAR because it is based on NuSTAR, which is a flying X-ray telescope that has been up in space for more than 10 years. So we instantiate the instrument, and as we want to be able to change the energy of the impinging radiation, we make these add parameters called E and E0 and DE, just to make sure that we can change the energy while we run the instrument. Okay, so that's done. Now, this simulation relies on, as I mentioned before, it's a large number of mirrors, but at least it depends on some data files being present. And these files basically are something that you can get from literature. There are plenty of papers written about NuSTAR. So this is what I've done. I've made them available in the GitHub repository. It's simply a matter of reading these files in. I've included a sample of what the format is. That's not so important. But the interesting thing here, with McStasScript, you can simply use normal Python line reading logic and read these data files in 2x2 lines of code. Also, I've defined a bunch of reflectivity files that contain reflectivities for the various coatings for all of these mirrors. These are things that you can also figure out from literature what they are. These coating files are also available on the GitHub repository. I should also mention that the coatings are highly optimized. These are not. These are something that I've done myself from what I can read, what I could read in the literature. This is an example simulation. This is not going to be as good as what is actually flying, but it's a starting point, and you can certainly change these, replace these files by something better if you want to. So let's just run this cell. That reads the data files and defines data file names for the coatings. An X-ray photon source. Actually, we access the help component here to see what parameters do we need to put to a source. This is something that you can do for any kind of object in McStasScript or in McXtrace as such. So now we instantiate the source. It's a source div. That it means a source with a controlled and defined divergence. For space simulations, it makes sense to have a zero divergence source. And we do this by setting a few parameters. It's a very large source, at least compared to beamline optics. So it's 1 by 1 meter, and it has no divergence, which means that it's extremely far away, which makes sense for space. And we also point the energy range to the parameter we just defined before. This that I've done in 7 lines of code, it could also be defined directly as a Python dictionary in 1 line of code, which we'll be using later to compact it even further. So now we need to also add some monitors to monitor the incoming radiation. We need it for computing the effective area of the telescope later on. So now we're going to come to the interesting part where we add the optics. And first, just for convenience, I add a reference point for the optic, which is which is here, the optic midpoint arm. And then I do a Python loop, looping over the data files that we read before in 133 steps. And that's as simple as doing this. And now we've defined the primary optic, which is the first bunch of mirrors in a Volter 1 type telescope. And we do the similar thing again for the secondary optic. And now we've actually managed to build our entire telescope optic just using these two small loops. And we're almost done. We now want to monitor the outgoing radiation. So we add a couple of monitors to that effect. And just for kicks, we could also add a monitor at the focal point. This is what we do here. So now we're actually clear to run the full experiment. That's all it takes to run a complete telescope, which I will be doing now. This may take a little bit of time because a C code is assembled and then compiled, and the compile step is going to take a little bit of time because we have over 500 components in this simulation, or devices, as each mirror counts as a device or a component. So I'll do that. Okay, so now we've done. The simulation has been done. You can see here it generates some output. A new C file has been regenerated or generated, and that we open these data files containing the coatings and so on. Now we can plot the data that we have recorded, which we do by running this here. This is simply an overview plot. You can see from the first plot that it's more or less constant, going from minus 0.5 to 0.5 meters in X and Y. That's just a flat monitor monitoring the flat square source. You can see there's no change in energy. And then we have the monitors coming after the optic, where you can see that this optic has obviously a circular aperture, and that indeed it imposes an energy dependence. And if you look very closely here, you can see that it certainly focuses the light onto a point or a very small area. Now, one thing that is very useful when McStasScript is that the data blob is returned contains NumPy arrays, which you can use for data analysis later on. And here I've just done the simplest thing that you could think of, is basically extracting the effective area of this telescope, which I will be doing by running this cell. And this is then a simulation, a ray-traced simulation of the effective area as a function of energy for the NuSTAR telescope with these coatings that I have defined. That was just about the demo that I wanted to show you here today. I definitely intend to contribute to McStasScript. One thing that I think could make it even more, if you will, Pythonic, is that at present the standard way of interacting with things is by adding one by one components to a list. And I think that perhaps a more Pythonic way of doing it would be to build your object as a Python instance of a component, and then later on assemble the through Python looping or script or listing, assemble these things as an instrument. That is one thing that I perhaps could make it more accessible to Python programmers that are not used to, that have not really seen the way McXtrace and McStas work. Another thing, perhaps even more useful or even more important, that I intend to contribute is to connect this kind of simulation or McStasScript with another astronomy community package called Pixel that simulates actual detector responses, so that you will get a point spread function that is related to the physics of the actual detector that you're intending to use to also improve realism in your simulations.